Hello everyone and welcome back to another video. And what we're going to do is just play around a little bit with our gamma functions and variants on that. So we're going to be messing with digamma functions as well. So without further ado, let's start with our good old friend, the gamma function right here, which is defined as the following integral. Now one of the main properties of the gamma function is this right here, the fact that x times gamma of x is equal to gamma of x plus 1. Now we could prove this using factorials, but perhaps a little bit more rigorously. What we can do is exploit the integral right here and prove it that way. So what we can do is consider x times the integral from 0 to infinity of t to the x minus 1 e to the minus t, and then times dt. And this right here is rather straightforward. We can just integrate by parts. We can integrate this t term and then just differentiate the e term, right? So what this is going to look like is something along the lines of, well, x times all of this, of course. But integrating the t term, we see that we have 1 over t times t to the x, and then times e to the minus t. Evaluated from 0 to infinity, of course. And then we have minus, so minus the integral from 0 to infinity of the derivative of rt, but that's just going to be an extra minus sign, so this is going to become a plus. And what we get is just, well, this right here, because the derivative of e to the minus t, once we get rid of the minus sign, it's just the same thing. So we have, or I do apologize, this should be an x right here. Whoopsies. And that should be an x. But we have is just that right there. So 1 over x times t to the x, and then times e to the minus t dt. Close the parentheses, and you'll see that this x right here cancels with all this, and the fact that the limit of this right here as we go to either infinity or 0 is just 0. So this term right here is in fact just 0. That right there is 0, leaving us with this right here, which by definition is gamma of x plus 1, as you can check using that right there. So now that was kind of cool, but let's consider another function, right? Let's consider the derivative of the gamma function and then divide that by the gamma function itself. What kind of properties would this function right here have? Well, one way we can express it is actually by the derivative with respect to x of the natural log of the gamma function. That's one way to express that equivalently. But this actually has a name right here. This function right here is actually called the digamma function. It's represented by a psi of x right here, and then equal to. Now what kind of properties would this right here have? Well, we know that for gamma of x plus 1, we can represent that as, well, x times gamma of x. So what properties would this digamma function have? So let's consider gamma of, psi of x plus 1, or digamma of x plus 1. So this right here is going to equal, just plain and simple, the derivative of the gamma function of x plus 1, and then divided by gamma of x plus 1, but we know we can just express that as gamma of x times x, or x gamma x. Now let's consider this term right here. Let's really investigate it, this gamma prime term. The derivative of the gamma function is equal to this right here. So the derivative of the gamma function from 0 to infinity of t to the x minus 1, and then times e to the minus t dt. Because this integral does not in fact depend on x, we're integrating with respect to t after all, we can just put this derivative inside the integral, and what we obtain is just, well, the derivative of, with respect to x, of t to the x. That's the only term we actually have to differentiate, and we just end up with an extra natural log of t inside the integral. So what we have is actually the integral from 0 to infinity of t to the x minus 1 e to the minus t, and then times the natural log of t, with respect to t, of course. And we'll see here that this right here is just gamma prime of x, but we need to consider gamma prime of x plus 1. So one thing that we can do is just make x equal to x plus 1, and you see that the minus 1s go away. So now what we're going to do is do integration by parts on this right here. What we're going to do is integrate our e to the minus t, and then differentiate our t to the x times natural log of t. Now, the way I chose this is because, well, I don't really want to be integrating any natural log terms, to be quite frank. That would get ugly quite fast. And we also know how to differentiate natural log quite easily because the derivative of natural log is just 1 over t. So we can get some terms just on their own right there. So actually integrating, we find that this right here, I'll zoom in, this right here is equal to minus e to the minus t, because that's the part we integrated, and then times t to the x natural log of t. And then we're going to have plus, because, well, we have that minus sign out front from the e, the integral from 0 to infinity of e to the minus t, but then we have the derivative of t to the x times natural log t with respect to t. So this right here is just going to be product rule, but starting with the t term, we have x times t to the x minus 1 times natural log of t. And then for the next term, we just had a plus t to the x minus 1 because, well, the natural derivative of natural log is 1 over t in this case, so we subtract 1 from the exponent there. This right here is quite interesting. Let's start with looking at this right here, this first term, where we're evaluating it from 0 to infinity. Assuming that x is some positive number, perhaps I'll do more analytic continuation or extension of the gamma function in a later video. But assuming x is greater than 0, the limit of this as it approaches 0 is just going to be 0. And same thing for infinity. It should be a bit clearer that the limit as it goes to infinity is just 0. So this right here in its entirety is just a big fat 0. But this right here we can actually separate into two different integrals. The first one is going to be factoring out the x out front. We're going to have an x times the integral, of course, and then times e to the minus t times t to the x minus 1 times natural log of t dt, and then plus this next integral, which is just going to be the integral from 0 to infinity of e to the minus t, and then times t to the x minus 1 with respect to t, of course. And we know how to evaluate, quote unquote, or at least give names to both of these integrals. We know that this first one right here, if we factor in the x a little bit later, this first one right here is just going to be the derivative of the gamma function at x, and then times x, of course. But then we have this additional term. We have a plus, well, this right here is just, by definition, gamma of x. So plugging this into our original formula, we see that we have the following. We now have that gamma, or x times gamma prime, of x plus gamma of x, all divided by x times gamma of x. And you'll see that we can separate this into two different terms. One term being gamma prime of x divided by gamma of x, and then we have another term that's just 1 over x. But this term right here is just the digamma function itself. So really what this is in its entirety is just digamma of x plus 1 over x. And this right here, as you said before, is equal to digamma of x plus 1. And this right here is one of the recurrence relations for the digamma function. Now that we have this relationship right here, we can use it to find some pretty interesting other results. So let's consider, for example, what digamma of 2 is. Well, this right here is just going to be equal to digamma of 1 and then plus 1 over 1, which is just going to be 1. So this right here is digamma of 1 plus 1. Okay, cool. Now what's digamma of 2? Well, digamma of 3. Digamma of 3 is equal to, well, digamma of 2 and then just plus 1 over 2. But we know that digamma of 2 is equal to digamma of 1 plus 1. So substituting this in, we see that we have digamma of 1 plus 1 plus 1/2. I'm not going to put the 1 and all the fractions together because there's a very cool pattern that emerges. And then for this next one, we have digamma of 4, which is equal to digamma of 3. And then plus 1/3, but we know that digamma of 3 is just all of this right here. So plugging this in, we see that we have digamma of 1 plus 1 plus 1/2 plus 1/3. And now to really hammer home the pattern here, we can have digamma of 5, which is equal to digamma of 4, and then plus 1 over 4, which, substituting everything in, we see is just equal to digamma of 1 plus 1 plus 2, or sorry, 1/2 plus 1/3, and then finally plus 1/4. And the pattern here is very clear. These right here are just the harmonic numbers. This right here is going to be the n minus 1, or rather the x minus 1, pardon me, rather the x minus 1 harmonic number. So if we have 2, the first harmonic number is just 1, right? Whereas we plug in 3, we have 1 plus 1/2, and that's just the second harmonic number. So one way we can actually represent this right here is by this right here. We can just say that digamma of x is equal to digamma of 1, and then plus the x minus 1th harmonic number. One quick note about digamma of 1. In this video, we're going to be taking it as a given that digamma of 1 is equal to the negative of the Euler-Mascheroni constant. I'll probably go into this in future videos, but just for the sake of this one, we're going to be taking it as a given that this right here is just minus gamma right there. Minus the Euler-Mascheroni constant. But going further into this harmonic number term right here, let's think of another way to represent this so that maybe we can get this digamma function in terms of a series. So one way to represent the harmonic numbers, so these right here, is equal to just the sum from k equals 1 to x minus 1 in this case, of 1 over k. And here, of course, x only applies for integers, for now, at least. One way to represent the sum right here is actually, instead of summing from k equals 1 all the way up to x minus 1, we can think of it kind of counterintuitively, but this works nevertheless. We can think of this, instead of the sum from k equals 1 to x minus 1, we can think of it as the sum from k equals 1 all the way up to infinity of 1 over k, but then just minus the sum from k equals x all the way up to infinity of 1 over x. And as I've written it now, this statement is not necessarily true. This is just sort of to get an intuition for it. Both of these sums do technically diverge, but if we put the terms together and group them in the proper way, it will actually not. One way we can reindex the sum is by summing instead from k equals 1 all the way up to infinity. And this right here means that we just have the sum from 1 over k minus x, sorry, k plus x, and then just minus 1. You'll see here that if we plug in 1 for k, we end up with a 1 over x, which is just what we started with. So one way we can represent this these harmonic numbers is by the following sum. This is the sum from k equals 1 to infinity of 1 over k, and then just minus 1 over k plus x minus 1. And now here's the interesting thing. This argument does not actually rely on x being an integer. We could plug in 1/2 here, and in fact, what happens is that we can plug in numbers that are not integers, and this formula remains valid. So one way to actually represent the digamma function is by this right here, and then just minus our Euler-Mascheroni constant. So this right here is just equal to the digamma function of x. There are a couple more identities that I am going to prove, but those are going to have to wait until next video, where we're going to be investigating a very fun integral and making use of the results of this video right here. So, for the sake of this not being 30 minutes, or even 40, thank you all for watching, and I will see you all in the next one.